What is up? Today we're going to start working on what these graphs of these trig functions really look like. Right? So let's look at one real quick and let's remember what our unit circle is. Okay, so what we are going to be doing is we are going to be using this unit circle to graph one period of the function sine. Right? So let's throw a little axis on here. All right, so notice this is just one of your regular XY kind of an axes that we've got. Only on the x-axis right here, instead of having our normal numbers like 0, 1, 2, 3, and so on, I've put these radian values on here. Okay. All right, so let's see how we can start graphing these things. So remember, if you go with these ordered pairs, right, the first one is cosine and the second one is sine. So what this first one says is that sine of 0 equals 0. So at 0 radians, my height is 0. Okay? At pi over 2 radians, my height is 1. Right? And we could do some things in the middle here. For instance, at pi over 4 radians, then the sine value is square root of 2 over 2, which is about 0.7-ish, something like that. Right? At 3 pi over 4, the sine value is square root of 2 over 2 again. At the value pi, my sine is 0. At 5 pi over 4, my sine value is negative 0.7. At 3 pi over 2, my sine value is negative 1. At 7 pi over 4, I get negative square root of 3 over 2 again. And then we get all the way back here to the beginning at 2 pi, my sine value is 0. Right? So if we graph all of these points together, this is what we get when we go around the unit circle one time. Okay? All right, and if you go one trip around the unit circle, that is called one period of sine. Of course, if you're graphing cosine, which we'll do here in a minute, that'd be one period of sine. Okay? All right, and then if you notice some other things we can define here, at this high point, right there, that has a distance of 1. And if we go down here to this low point, it has a distance of negative 1. Right? That is called the amplitude. Right? And in this case, it's just the absolute value of 1 or the absolute value of negative 1, which still just gives me 1. So again, the amplitude is the distance from the middle of the graph to either the high point or the low point, right? And we are 1 unit up or 1 unit down, so the amplitude is just 1. Okay? Obviously, if you look at this thing, the maximum value, the highest value we have is 1. The lowest value, the minimum, is negative 1. Okay? So this is what y equals sine of x looks like when x is between 0 and 2 pi. Okay? Of course, if we wanted to, we could go backwards in the other direction, and it would just be a straight-up copy of this thing. Right? So if I went and copied this thing, it would look something, whoa, really not like that at all. Right? So let's see. So if we start here at 0 and go back in this direction, negative pi over 4 would give me negative square root of 2 over 2. Right? At negative pi over 2, I get negative 1. And so on for all of these. Right? And then if you notice when we connect the dots, it looks exactly like that green one, like the Christmas look I got here. Looks exactly like that green one. So really, all these coterminals that we've been making, where we keep on adding 2 pi to them or subtracting 2 pi to them, what that does is it takes this one period of sine length of the sine function that we've got right here, and it just copies it all the way down the x-axis and all the way up the x-axis. So if we wanted a true picture of what sine looks like, what we could do is draw a long old x-axis. Right? Here was one period of sine of x. Right? And then we could make another period of sine x, right? And then make another period of sine x, right? And then do the same thing on this side, and so on, right? It just keeps on going and going and going. And sine of x, this function all by itself, the biggest it ever is 1, and the smallest it is -1, right? So what we say here is that sine of x oscillates between 1 and -1. Okay? So if we go back to this, again, that's kind of a better picture of sine. And where do these points come from? They come from my unit circle right here. Right? So let's see if we can get an idea of what cosine of x is going to look like. Right? All right, so now let's graph the function f of x equals cosine of x. Right? And we'll do the same thing we just did. Let's just go around our unit circle for that first period. Right? So here, let's start off right here at 0. Right? Cosine of 0 is 1, so it's going to start right there. Let's see. Cosine of pi over 4 is square root of 2 over 2. Cosine of pi over 2 is 0. Cosine of 3 pi over 4 is negative square root of 2 over 2. Cosine of pi is -1. At 5 pi over 4, we get negative square root of 2 over 2. At 3 pi over 2, I get a cosine value of 0. At 7 pi over 4, this one right here, I get a cosine value of square root of 2 over 2. And then when I get all the way back here to the beginning at 2 pi, my cosine value is 1. So it looks something like this thing. Okay. So again, what we've drawn here is one period of cosine x. Right? If you notice here, we went all the way from 0 to 2 pi around the unit circle. So the period length here equals 2 pi. Right? That's the distance from the start to the end right there. Right? So that distance is 2 pi. That's the period length. Okay. Let's see here also the amplitude. All right, so if you go from the middle of the graph to the outer edge, right, either here or maybe here, the amplitude is still a distance of 1. Okay. This one has a maximum value of 1. Right? You can see that occurs right here. And it has a minimum value equal to -1, which happens right there. Right? So just like sine of x, cosine of x always oscillates between 1 and -1. Right? And then what we could do is, again, to get a complete picture of this, I could take this picture and just copy it all the way down here to the left. So make a whole bunch of copies here to the left, make a whole bunch of copies here to the right, and just keep on going all the way to infinity and beyond there. Right? So again, the part in red here, right, again, that is a graph of one period of cosine of x. Right? So if you notice, cosine of x and sine of x actually look pretty close to each other. Right? So let's look at these two things. All right, so if you remember, when we graphed f of x equals sine of x, it looked kind of like this thing. Right? And it went up like this and down like that. All right. So again, this is one period of sine x. When we graphed cosine x, it started up here at 1 and went down like this. Let's see. 0 pi to 2 pi right there. So it went something that looked like this. All right, so that's what the function g of x equals cosine of x looks like. Right? So again, in green here, this is 1 period of cosine of x. Okay. Again, what we could do is take these functions and again just start copying them up and down the x-axis. Do the same thing for these red ones. Of course, it needs to be a little bit more scientific than that, but that's kind of what we can do. Because again, these functions just keep on going all the way to infinity here. Okay. All right. So that's what the basic shape is that I want you all to be thinking about. Okay. All right. So when you think of the function sine of x, just regular old sine of x, not shifted up, down, left, right, or anything. We'll do that here in a minute. All right. Remember, it should look something like this thing. Okay. That's what sine of x should look like. And for cosine of x, right, it's going to look something kind of like this. Right? So that's cosine of x. Again, those things just those points came straight from the unit circle. And like I said, we could make an infinite number of copies of these things, just keep on going and going. Just let them oscillate, to and from infinity. And they just keep on going like that. Okay. All right, so the key words here that we've seen so far is the period. Right? That's where one of these portions, well, let me say that again. This is just the length of one copy of the function. Okay. So when I had my sine function that looked like this, that's one copy of the function, and it started at 0, it ended at 2 pi, so the period length here is just 2 pi minus 0, which is 2 pi. Okay. We also saw the word amplitude. Okay. This is the distance from the middle of my sine function to the highest or lowest point. All right, so here I could measure the amplitude like this, or I could take this point and measure the amplitude like that. Either way, they're both a distance of 1 in this case. So the amplitude equals 1 for this particular function. Right. Of course, the maximum value, that's just the highest point. And in this case, the highest point is right there when my function value is 1. Right? The minimum equals the lowest point, which in this case, that happens right here, and that equals -1. Okay? So what we're going to do now is what we have been doing with other functions. We're going to start shifting these things all over the place. Right? So let's think about what a plain sine function looks like. All right. So again, let's remember what y equals sine of x looks like. Right? It looks like this thing. Like this. Okay. Let's remember what our shifting techniques do for us. Okay. So for instance, if I have f of x plus a, that shifts my picture up by a units. Okay? So if I wanted to graph y equals sine of x plus 2, what that's going to do is going to take my sine of x and make it go up by 2 spots. So this point 0, 0 gets bumped up here to 0, 2. Pi over 2, 1 gets bumped up here to pi over 2, 3. Pi 0 gets bumped up to pi 2. This one gets bumped up to 1. That one gets bumped back up to 2. And it'll look like this thing. So again, I literally just took every point and pushed it up by a units. Okay? So that is a vertical shift upwards. Okay? So again, this is a vertical shift because we lifted our graph up vertically. All right? On the same token, if I had y equals sine of x minus 1, then we will go down 1 with my function sine of x. So this point 0, 0 gets pushed down here to 0, 1. Pi over 2, 1 gets pushed down to pi over 2, 0. That gets pushed to there, there, and there. And it will look like this thing. Okay. So again, that's another example of a vertical shift. But in this case, that was a vertical shift that went down. Okay. All right. So again, for this shifting up and shifting down, the vertical shifts, it's just f of x, whatever our function is, plus or minus some value a. If it's positive, it goes up a units. If it's negative, it goes down a units. Right? So remember, this one is the function sine of x. The red one is my function sine of x plus 2. I just shifted it up 2 spots. And then the blue one here was, I took this function sine of x and I pushed everything down 1 spot. Okay. All right, so that's shifting it up and down. What about left and right? All right, so when we've wanted to shift something left and right, we've looked at either f of x plus a or f of x minus a, right? And we've called these things horizontal shifts. Right? When it comes to trig functions, these have a fancy schmancy name to them. These are called phase shifts. I know, right? But phase shifts are what these are called. Right? And if you remember, these do kind of the opposite of what you think they would do. Right? This one actually goes to the left by a units. This one goes to the right by a units. Okay? So let's look at this function. How about f of x equals cosine of x? If you remember, that looks like this thing. Right? So there's my function cosine of x. Right? What if I had this function? How about g of x equals cosine of x? How about plus pi over 2? Right? What we'll do is we'll take that function cosine x and push it left by pi over 2 units. So this point at 0, 1, it gets pushed over here to the left by pi over 2 units to there. This point at pi over 2, 0 gets pushed left to there. This point gets pushed to there. That one goes to there. And this one goes to here. Right? And it's going to look something like this. Okay? So again, that green one, that is cosine of x plus pi over 2. All right? We can also go the other direction. Let's say I have this function h equals cosine of x plus pi. Then what I will do, and well, I'm going to run out of room here, but I'm going to take every point from my cosine function and I'm going to move it to the right by pi. So this point right there, that point 0, 1, that's going to get moved to the point pi comma 1. So it'll get moved to here. Right? And then we'll do the same thing for all of these other points, and it will look something like this. Right? And this blue one, that is cosine of x plus pi. All right. So again, if you add or subtract something on the outside, it's a vertical or a vertical shift up or down. If you add something inside your function with your x and your cosine, then that's a phase shift to the left or to the right. All right. And let's look at one more. What if I gave you this particular function? How about y equals sine of 2x minus pi over 6? Okay. If you remember how we're supposed to do these, well, I tell you what, hold off on that thought just for a second. let's just go with 2 pi first. Okay. Remember, what we do here is when it's on the inside with the x's, we are going to divide each x value, in this case, by that number 2. All right. So here is my function sine of x. So this function y equals sine of 2x, we'll take all these points and divide the x value by 2. Right? So 0, 0 will become 0, 0. The point pi over 2 comma 1, divide that x value by 2 or multiply it by a half, gives me pi over 4 comma 1. Right there. The point pi comma 0, multiply that x value by a half will give me 1/2 pi comma 0. So that'll be right to there. And then this other point gets shifted to 3 pi over 4. This one gets pushed to pi. So it looks like this thing. And just to remind you of the rule, if I have f of a times x, again, what we're going to do is we're going to divide each x value by that number a. Right? If a is bigger than 1, then we are compressing this graph. Right? And if a is between 0 and 1, then we wind up stretching the graph. Right, and here's that last one I was going to show you. What if I had y equals sine of 2 times x plus pi over 6? Now, I'm sorry. Let me make that pi over 3. I think that's what I had before. All right, so in red here, I've got one period of the function f of x equals sine of x. Okay. All right, so let's think about what this is going to be. Remember, in these cases, the strategy that we were trying to use was, first of all, to factor the inside. So I'll factor a 2 out to get this. Right? And now let's just go from the inside and work our way out. Right? This says to take the graph and move it left by pi over 6 units. And then that says to divide the x value by 2. Okay, so we're going to compress it by a factor of 2 and move it left by a factor of pi over 6. And this point 0 over 0, or 0 comma 0, it's going to become, well, if we move it left by pi over 6, that'll be negative pi over 6 comma 0. And then if I divide that by 2, that's, let's see, negative pi over 12 comma 0. The original point, pi over 2 comma 1. If we move it left by pi over 6, that's 3 pi over 6 minus 1 pi over 6 is 2 pi over 6, which is pi over 3. That's if I move it left by pi over 6, and then I will divide the x value by 2, and that will give me pi over 6 comma 1. So this point, pi over 2 comma 1, that's going to get shifted to pi over 6 comma 1. Okay? And all of these other points are going to get shifted as well. So let's go to this last point, 2 pi comma 0. Here I will shift it left by pi over 6, so that's 12 pi over 6 minus 1 more gives me 11 pi over 6 comma 0. And then if I divide the x value by 2, I get 11 pi over 12 comma 0. So this point gets shifted to 11 pi over 2 comma 0, and it's going to look something like this. Okay. So it got compressed because of the 2, and it got shifted to the left because of the plus pi over 6. All right, so just to remind you, what you might want to do is to review the unit circle. Right? we need to review our shifting techniques. Right? And let's learn these new terms: period for the period length, the amplitude, the maximum value, the minimum value, and also these fancy words, phase shift and vertical shifts. All right, so make sure you review some of those things before you come to class, okay? All right, so I hope that you guys will watch all of this so that we can be ready for class. And I think that's all I really have for you all right now. We'll do a lot of these in class on Monday, and we'll be working on the stuff at least through Wednesdays too. So I will see you later.